This is lecture 25, yes. In lecture 24, we looked at objects, solids, and we studied the basic laws of their thermal properties, basic thermal properties. What I want to do today is I want to look at gases. So let's pretend that instead of this brick, I have some sort of cylinder and I have a gas in the cylinder. This gas is made of molecules. The molecules move around. There is energy in this motion. And if I put more heat into the cylinder, then my molecules will be moving faster and the temperature will go up. This is very similar to how solids behave, but one difference with gases is that they exhibit much richer behavior. One of the reasons is that gases, unlike solids, don't preserve shape. So in addition to absorbing heat and giving away heat, and in addition to temperature going up and down, we have other degrees of freedom. The volume of this gas, for example, could change. If I have a cylinder here, the top of the cylinder could be moving. It could be moving up and down. That will change the volume, and as we will see later, the change in volume will affect thermodynamical properties. So first, let's start thinking about this cylinder full of gas and how to describe its state. In the first half of our class, we were mostly concerned with point particles and how point particles moved. Then we looked at extended objects, and we looked at how extended objects rotated and moved at the same time. For particles, to describe where they were, only three numbers were necessary. X, Y, Z coordinates would describe position of a point particle, and position of a point particle is really the only thing about that particle. If you know how X, Y, and Z change with time, then you know how the state of this particle changes. With the gas, things are kind of not as simple. In principle, we could look at every single molecule and we could write down X, Y, and Z coordinates of every single molecule. But because there are quadrillions of molecules in even a very small piece of matter, this would be impractical. So what we do instead is we try to describe the state of this gas by some numbers that collectively describe the state of all of the molecules. So one such parameter is volume. We already mentioned volume. This gas is constrained within some volume, cubic meters. This volume could increase and it could decrease. Since we have finite volume, the molecules of the gas will be constantly colliding with the walls. And as they collide with the walls, they will be exerting some pressure. So then there is pressure. We can measure it in pascals. And then there is this energy, the energy of collective, the net energy of the motion of the molecules. And we know that temperature is a kind of proxy for that energy. So we have temperature, and we will measure it in degrees. Let's say degrees of Kelvin. And the thing about these properties, volume, pressure, and temperature, is that they're not necessarily independent. So for example, if you have this cylinder, if you put it on a stove, and if you heat up the gas, then its temperature will go up, but then its pressure will also go up because there will be more, when the molecules collide with the walls, they will be colliding with higher velocity, and that will result in a larger net force. So there will be higher pressure. But we'll talk about those things later. So for now, we will stick to these three numbers: volume, pressure, and temperature. And to describe the state of the this piece of this gas in the cylinder, what we will often do is we will often draw pressure versus volume diagrams. I can draw a pressure versus volume diagram like this, where I have volume on my horizontal axis and pressure on my vertical axis. So this could be 0, 1, 2, 3, I don't know, 100, 200, 300. And if I have, if my gas has a volume of 2 cubic meters and a pressure of 100 pascals, then I can put this point here, and this point then would describe the properties of this cylinder of gas. So this is kind of like a coordinate for a particle. When I put down this point, I know exactly what the properties of my gas are. And if those properties change with time, then this point will trace out a line. So if I'm here, but if for some reason both my pressure and volume go up, then I will have a line like this. So this is my initial time. This could be after my state after 3 hours. And then if I keep my volume constant and if I drop my pressure, this line would go down like this. And so every any kind of change in the properties of my gas can be described by a line. And if I look at this line, I can read this line and I can know exactly what happened to my gas. So I'm now on slide number 3. I want to, for now, I want to ignore temperature and only look at volume and the pressure, because this volume and the pressure are kind of new things compared to the solids. So let's think about what exactly is happening if I have my gas in the cylinder and if the volume of this gas increases. For simplicity, I will draw it like so. I have my gas and then the top moves up, so I have a longer cylinder now. So as we know, there are molecules. These molecules constantly collide. And when they collide with the walls, they exert a force. So there will be molecules colliding with the top of the cylinder, and they will be creating some sort of force, some sort of net force. Now, if this top of the cylinder moves up, this means that my molecules, my gas, applied force to the cylinder, and the cylinder moved. So I have force, I have displacement. And if I'm acting on something, and if that thing moves, then this means that I've done some work. So the net force of all the molecules colliding with the top of the cylinder times the displacement of the top of the cylinder is the amount of work that this gas did on its surroundings. Now it's more convenient to express force in terms of pressure. Just to remind you, pressure is force divided by the area. And so if I replace force by pressure, then I would have to write, instead of force, I would have to write pressure times the area. Pressure times the area times displacement is equal to work. And now area times displacement. So if you take the area of this top cylinder and if you multiply it by displacement, which is this extra height that you gained, then you will get the volume. So pressure times volume is the work. So let me circle this. Basically, what I'm trying to get at is that if you have gas in some volume, and if this volume increases, then gas does work on the surroundings. If the opposite happens, if you have a cylinder, and if the cylinder shrinks, if it gets smaller, then there must have been something outside in the surroundings that applied extra force and moved this top of the cylinder down. Since the molecules are still trying to push it up, and since this top is moving down, in this case, the pressure in the gas is working in the opposite direction of the motion. So in this case, gas will be doing negative work. So perhaps instead of volume, maybe I should write change in volume here. Let me write change in volume here. So pressure times change in volume is equal to the work that gas does. And if volume increases, gas does positive work. If the volume shrinks, gas does negative work. You can now think about what would happen if the pressure was changing. So let's say I have the cylinder, and let's say the top is moving up, giving me more and more volume. But as the top is moving up, my pressure is changing. So my pressure could be dropping, for example. After this top moved by 1 centimeter, my pressure is now less. So I used to have 10 pascals of pressure, but now I have 9. And for the next 1 centimeters, I'm acting with 9 pascals of pressure, but then my pressure would drop further. I could be in a situation where my volume is changing, but as my volume is changing, my pressure is also changing. So the amount of force isn't constant, the amount of force is variable. You can probably guess where this leads. When we talked about work, we saw that if the force was constant, then work was force times displacement. But if the force was variable, then instead you have to do integral over force times displacement. Similar logic applies here. So if you have varying pressure, if your pressure varies as your volume changes, then the amount of work that gas does on the surroundings is equal to the integral of pressure over volume. Let me circle this, put this in a box. Work is integral of pressure over volume. If you know exactly how your pressure changes, you can compute this integral. And if your pressure doesn't change, then the work is simply pressure times change in volume. So in your homework, there will be a couple of problems where you have to compute the amount of work. So let's say this is my pressure versus volume graph. And let's say on this graph, I have gas that was here, but then its volume increased and its pressure dropped. So this gas is moving in this direction. Less pressure, more volume. And if I want to find how much work was performed from this point to this point, then I have to compute integral of my pressure with respect to volume. And we all know what that is. Graphically, that's area under the curve. So if they ask you to compute work that the gas does when it moves from this state to this other state, from state A to state B, then all you have to do is you have to compute this area under the curve. Now, the thing about this work is that this work kind of depends on how you move from A to B. I could move from A to B like this. So I could first increase my volume by keeping my pressure constant. until I have this desired volume. And then I could drop the pressure as I keep my volume constant, like so. And if I did that, then my work now would be area under this new curve, the red curve, and you can clearly see that this area is larger. So my gas would have to perform more work to move like this. So what this means is that if you have a piston, so if you have a cylinder, and if you have a gas in the cylinder, and if this piston moves up, then how much work gas has to do in this motion kind of depends on what happens in between. You cannot just tell how much work your gas did just based on your initial and final positions. So very often you will have loops. You have a loop when you have gas at some pressure and some volume, and then there are some changes, and then there are other changes, and in the end you get back to your original state. So you could have this piston here, the cylinder, and the cylinder could be here, the top of the cylinder could be here initially, and then it could move up somehow, and if it moves down, back to this position. And if you have exactly the same pressure when it gets back, then you have completed a loop on this graph of pressure versus volume. Now the question is, when you complete a loop, if you get back to your original position, does this mean that you have done no work? And the answer to that question is that not necessarily. So let's see how that works. So I started from here, from A, and then my pressure increased, my volume increased, and then my pressure dropped, and then my volume dropped, and I got back to this point A. So now what I will do is I will pick an arbitrary point here. Let me pick this point and let me call this point B. And so the work that I did during the cycle is the work that I did when I moved from A to B, plus the work that I did when I got back from B to A. The work that I did from A to B is positive, and the work that I did from B to A is negative. And that's, simply because of the way the integral works. If you're taking integral from 1 to 2, you will have a positive sign, but if you switch the limits, and if you take an integral from 2 to 1 instead, then you will get this negative sign. So this is positive work, this is negative work. And the work that I did from when I moved from A to B is the area under this top curve, okay, under this top curve. But the work that I did when I moved from B to A, the negative work, is the area under this green, under this bottom curve. So I will color it in green. So what I will have to do for the cycle, if I'm asked to compute work for the cycle, what I will have to do is I will have to take the yellow area, subtract the green area, and then the leftover is this red area in the middle. So the total work in this case will be positive, and it will be equal to the area encircled by this cycle. And it doesn't matter what kind of cycle I have. If they ask me for net work, I have to find area inside the cycle, and that's the amount of work that I did. There are many examples in the textbook of this. I don't have nearly enough time to go over all of the examples because I'm at a 20-minute mark now, but I would strongly encourage you to read these chapters in your textbook. Okay, so this was work. Now, when volume changes, my gas does some work. This work could be negative or positive. So that's the takeaway point. Now let's think about what happens if my volume is fixed, and so let me draw the cylinder again. If my volume is fixed, what else could I do? How can I affect this gas? Well, I can always affect it by pumping some heat into it. I could move some thermal energy into it, or I could cool it down by taking away some thermal energy. I know that if I put pump some heat into it, so heat into it, then the internal energy of my gas will go up. There is some internal energy, and if I put heat in here, the internal energy will go up. And if I take away heat from here, then the internal energy will go down. So that's simple. Now the question is, what will happen if I put some heat into the cylinder, but at the same time the cylinder grows in size or shrinks? So what happens if I have heat flow, but at the same time I have change in volume, which means I have some work? If there is no work, then the amount of heat that I put into the system is equal to the change in its energy. The heat is usually noted by capital letter Q. So the amount of heat is that I put is change in internal energy. So if I put heat with a positive sign, then my energy increases. If I take away heat with a negative sign, then my energy goes down. But if at the same time my gas is doing some work on the surroundings, then we know that you cannot just do work out of nothing. You have to spend energy to do work. So some of this energy will be spent on the work. So what happens here is that I put heat, the energy of the gas goes up, but then this gas does work, and it spends some of its energy. And in the end, the equation that describes this process is a very fundamental equation called the first law of thermodynamics. And this equation reads Q is equal to the change in internal energy plus work performed by gas. So I will frame this equation because it's a very important equation. I have been talking about gases here, but this equation is more fundamental than that. This equation actually applies to everything. It doesn't have to be gas. It could be any thermodynamical system. And I mean, intuitively, it's kind of simple to understand and to believe this equation. This equation tells you that if you give some heat thermal energy to a system, then this thermal energy will be spent on increasing the internal energy of the system, and some of it could be spent by the work that the system does. And the sum of these two terms has to be equal to the energy that went in. So the first law of thermodynamics is basically just a version of the energy conservation. This equation tells us that the energy is conserved. You cannot have more energy than the energy you put in. So later I will solve a few problems that employ this law, the first law of thermodynamics. When you use the first law of thermodynamics, it's very important that you get your signs correct. So this Q is positive if you put the heat into the system, and this is negative if you take away the heat from the system. The change in energy is positive, obviously, if the energy goes up, and it's negative if the energy goes down. And the work is positive if it's the gas that's doing work. And the work is negative if it's the surroundings that do work, and if gas is working against the change. So if the volume goes up, you have a plus sign here. If the volume goes down, you have a minus sign here. Your textbook gives many examples of this. Let's go through a few examples. On my slide number 5, I have this pressure versus volume graph. And on this graph, I have this initial state and the final state. So my gas had some pressure and some volume here, and then it changed its pressure and it changed its volume, so it moved to this point. And the figure shows multiple paths to do this. So this is path 1, path 2, path 3, and path 4. When you look at this kind of graphs, you should be able to answer some simple questions. So for example, if I ask you which path results in the most work done by the system, then if you think about this, you should be able to guess that it's path number 4, because work is integral of P dV. Integral is area under the curve, and it's path number 4 that gives you the most area under the curve. Let me redraw this P versus V here. There are some special kinds of changes of states that have their own names. So let me also write the first law of thermodynamics here. Q is equal to the change in internal energy plus work. So first of all, if I'm, for example, at this point, and if I simply drop my pressure, or if I increase my pressure, but if I do this without changing my volume, so I just go up and down, then this is a case of fixed walls, fixed volume. And in this case, my work is 0. So if volume doesn't change, there is no work. And in that case, the amount of heat that I put into the system, all of this heat goes into increasing the energy. If I have a system, again, let's say I have a gas in a cylinder that's insulated from outside so that there is no heat going in and out, then this term will be 0, this Q will be 0. And if the Q is 0, then my equation reads negative change in internal energy is equal to work. And what this equation means basically is that if there is no energy added to the system or taken away from the system, then if I want to do work, I have to spend my own internal energy. There are also cyclic processes. We talked about cyclic processes where I start from here and then I end up at the same place. And since I ended up in the same state, I must have the same energy. So then the change in my energy is 0. And if this is the case, if I have a cycle, if I get back to my original point, then the first law of thermodynamics reads Q is equal to W. Q is equal to W means that the work that I performed, which is the area enclosed inside this cycle, is equal to the amount of heat that I have taken from the surroundings. So if I have the same energy as I used to have, but if I ended up doing work, then this work must have come from somewhere, because otherwise the energy conservation would be violated. And this work is then performed because I absorbed heat from outside. So this is kind of what happens in car engines. In car engines, you have pistons and cylinders, and you have cycles where this piston moves up and down, and it returns to its original position. And when the piston returns to its original position, while it's doing this motion, it does some work. And it does this work because it gets heat from outside. There is fuel that is injected in here. The fuel is burned. There is some heat released, and it's that heat that allows you to do work. So I want to stop here with the first law of thermodynamics. This is not a simple concept. The concept itself is probably simple, but it may take some time to get used to it and to figure out how to use it in practice. Those kind of things are best done when interacting face-to-face, kind of in person. What I would like you to do is I would like you to look at your homework problems, and if you find it difficult to link this to your homework problems, then you should join the Zoom help room, where we will talk about this. I will walk you through your homework, and then hopefully some of the things will become clearer.